Hi students, welcome to the session on loss tangent. Right, so it's an important ratio. Let us see that. So loss tangent is the ratio of magnitude of conduction current density JC to the magnitude of displacement current density JD. So conduction current magnitude is given by sigma epsilon, sorry, mod sigma E. Displacement current magnitude is given by j omega epsilon E. Right. So as we have studied a phasor form of Maxwell's theorem, from that we know these things. So this indicates E cancel, mod j is 1, so it will be sigma by omega epsilon. Right. This sigma by omega epsilon is equal to that is JC, magnitude of JC is JC by JD is equal to sigma by omega epsilon, that is equal to tan theta, right? So this tan theta is known as loss tangent. So tan theta is equal to sigma by omega epsilon. This is known as loss tangent. So it's a ratio of magnitude of conduction current density to displacement current density. What is theta is? Theta is loss angle. So it's a loss angle. Okay. So loss angle of the medium. Okay, how we are going to illustrate? We see the theta. This is our loss angle. Side x-axis represents conduction current density. Y-axis represents displacement current density. Fine. So you see it is separate. This line is demarcating conductor and dielectric. You see this conduction current density, we know it is available only in conductor. In dielectric the current is due to displacement current, so it is dielectric. This line segregates conductor from dielectric, right? So but it is used to find how lossy the medium is, right? So okay, let us see in what way we are going to find. So loss tangents will, so it is used to determine how lossy the medium is. Okay, right? How lossy the medium. That is the use of loss tangent. Okay, so you see a medium is said to be good dielectric, right? So medium is said to be good dielectric here. Then what is the condition? Tan theta is very small, right? So tan theta is very small. Why? When tan theta is very small, when theta is small, tan theta will be very small. Theta small means it will be like this. So it is approaching dielectric. So medium is said to be good dielectric. Tan theta is very small. When a medium is said to be good conductor, when tan theta is very large. When theta is very large, what happens? This line will come towards here, right? So tan theta is very large. So when tan theta is very small, the medium is said to be dielectric. When tan theta is very large, the medium is said to be good conductor. You see what is tan theta from here? You see tan theta is equal to opposite. What is opposite side? Here it is sigma E means here also it is sigma E. So opposite by adjacent. What is adjacent here? Here adjacent is conductor j omega epsilon E. That's why it is loss tangent. So that's why we have drawn the diagram. For this equation we have drawn like this. Okay. So that's why this is equal to tan theta. You can ask why suddenly how you have brought this sigma by JC by JD is tan theta, because of this. So if theta is closer, that is theta is very small, tan theta is very small, the material acts as good dielectric. If it is large, it acts as a good conductor. So what happens, you see, for good dielectric theta, tan theta is very small. Tan theta very small means sigma must be lesser than omega epsilon. So sigma, so for dielectric, theta must be very small, so sigma must be far lesser than omega epsilon. Similarly, for conductor, tan theta must be large, so this value should be large. That means sigma must be greater than omega epsilon, right? So this is what the difference between the conductor and dielectric, right? So that we have to remember. Then also you see, if JC is greater than JD, right? That's what I told. If JC is greater than JD, what will happen, right? The angle will become pi by 2. Sorry, you see, when JC is far greater than JD, the total things will come here. The theta will be very large, so it will act like a conductor. So JC is greater than JD means it is a conductor. Fine. That is very important point. Then only sigma must be greater than omega epsilon, right? So that is what JC is greater than JD, it is conductor, and sigma must be far greater than omega epsilon. That means conductivity is very high, very high. Conductor should have conductivity of very high value. So that is a correct definition, right? So that is one important point. When conductivity is very high, we know, right, alpha and beta depends on conductivity, depends on sigma, right? That and all we know already. So when alpha and beta, when sigma value increases, alpha is also increase, right? That is the formula. We know, we remember what is the formula for alpha. Alpha is equal to omega into mu epsilon by 2 into 1 plus sigma by omega epsilon square minus 1. So what will happen? You see, when sigma increases, alpha increases. Similarly, beta is simply plus 1. So when sigma increases, beta increases. So when sigma increases, alpha attenuation increase, phase constant also increase. That is the main thing we have to remember. So you see, in conductor, the thing we have to notice, in conductor, JC is far greater than JD. We have only conduction current density, right? And sigma is far greater than omega epsilon, right? And what is the other thing we have to remember? Here, conductivity increases means alpha will increase and beta will increase. Similarly, for dielectric, everything is reverse. So theta should be very less. So JC must be less than JD, right? And sigma must be less than omega epsilon, right? So dielectric has poor conduction. So sigma is less, and we know the alpha tends to 0. Fine. So this is what we have to remember about last tangent, right? So it demarcates dielectric medium from conducting medium, right? So that's all about this session, right? If you have any doubt, please ask me in comment section. Thank you.